Hello everybody, welcome to lecture 6 in M8283 linear algebra. So today we're going to develop a little bit further our techniques and methods for solving systems of linear equations by applying elementary row operations to the augmented matrix. So just to recall a few of our definitions from last time, we talked about how to write the augmented matrix of a system of linear equations. So that's just the matrix which has in its rows the coefficients of the variables and also of the right-hand side in each of the equations in order. So the number of rows in the augmented matrix is the number of equations in our system, and the number of columns is one more than the number of variables because it's got one column for each variable and an additional one for the right-hand side of the system. Okay, and our basic strategy last time, which we kind of outlined in general at the end of the last lecture, was to apply elementary row operations to the augmented matrix to get it into what we refer to as row echelon form. So let's just recall what that means. And here on the slide, we have an example of a matrix which is in row echelon form. So it means, first of all, that within each row, the first entry that isn't a 0 is a 1. So we can observe here that in the first row, the first non-zero entry is a 1. The second row starts with a 0, but the first non-zero entry is a 1. And the third row starts with two zeros, and the first non-zero entry is a 1. So that's the first sort of requirement for being in row echelon form. Second one, as we travel downwards through the rows of the matrix from top to bottom, the so-called leading ones, which are these first non-zero entries of each of their rows, they should move from left to right as we travel downwards through the rows. So we shouldn't have any leading one further down being to the left of one that's above it. Third thing, in the columns below the leading ones, we should have nothing but zeros. So if we look at each of the leading ones there in that example, we can see that underneath them in their columns is nothing but zeros. We do have some non-zero entries above them. Okay, and a remark last time is that if two people take the same matrix and set about the problem of trying to reduce it to row echelon form using elementary row operations, they may well get different answers. There's no guarantee that they'll get the same answer because they have choices to make at different stages along the way about what operations they're going to apply in order to get their matrix into the desired form. So it is possible that the kind of area above the diagonal there of leading ones, you know, it's not uniquely determined by the matrix that you started with. And so the row echelon form is not fully determined by a given matrix. Of course, the two answers should be consistent with each other in the sense that if, for instance, they're used to solve systems of linear equations, the two developments at that stage should ultimately lead to the same answer. But yeah, but it's not true that every matrix has a unique row echelon form. The form that you end up with depends on the choices you make along the way, which maybe suggests potentially that it's possible to kind of push it a bit further, reduce a bit more, get it into a somehow even nicer or even simpler form. And that's what we're going to talk about here, and that is the reduced row echelon form. So the difference between a row echelon form and a reduced row echelon form is that in a reduced row echelon form, item 2 here, wherever you have a leading 1, all the entries in the same column as that leading one, not only below it, but above it as well, should be zeros. And I guess the observation here is that if you come to a row echelon form, as in this example, then you might observe at that stage that, well, if I look at the entries above the leading ones in this example, so there are 3 of them in this example, there's this one, there's that one, and there's that one. None of them are 0 currently. And remember, I should recall that what we mean by elementary row operations is elementary row operations on a matrix have 3 types. We can multiply a row by a non-zero constant. That means multiply every entry in the row by the non-zero constant. We can swap 2 rows, or we can add a scalar multiple of one row to another row. And we saw a general sort of strategy last time to get any matrix into row echelon form through a sequence of such operations. And the basic strategy was to get a 1 in the top left in the first place, then clear out the rest of the first column by adding or subtracting multiples of row 1 to subsequent rows, then move on to the second column, get a 1 in the position there where that second leading 1 is in this example, clear out the rest of column 2 below that, and so on. Proceed through the columns from left to right. And we didn't worry about anything that appeared above the leading ones. Of course, they were kind of changing along the way, but the designation of row echelon form doesn't require us to worry about anything that happens above the pattern of leading ones. But at this stage, when we do have a row echelon form, you might notice that if you look, for example, at this -1 here in the first position of column 2, you could eliminate that -1 and transform it to a 0 by adding row 2 to row 1. And that wouldn't damage anything in column 1 because we'd only be adding 0 in the first column. So we could actually go a bit further and clear out the entries above the leading ones as well as the entries below them. And this is the process of Gauss-Jordan elimination. It clears out all the columns where the leading ones are, both above and below. Similarly, with the 4 and the -1 here in column 3, we can reduce the 4 to a 0 by subtracting 4 times row 3 from row 2. That doesn't affect anything to the left of this 4 because of the 2 zeros in the first 2 positions here of row 3. And similarly, for the -1 up here, we could eliminate that if we wanted to by adding row 3 to row 1. So basically, by using the fact that the matrix is in row echelon form, we can now clear out not only the entries below the leading ones, but also above them by adding multiples of subsequent rows to higher rows. So let's do it for this example. I'll try to squeeze it into this line. So first step, we're going to look at column 2. It's not in, so the entries in column 2 are not consistent with the reduced row echelon form because there is a leading 1 there in position 2, but there's a non-zero entry above it. So to deal with that, we should replace we should add row 2 to row 1. So we should replace row 1 with row 1 plus row 2. And when we do that, in the positions of row 1, we're at each stage adding the entry in row 2 to the entry in row 1. So we get 1 plus 0, -1 plus 1, that's the 0 that we want, -1 plus 4, that's 3, so that changes, 2 plus 3, that's 5, and 0 plus 10. Because that's what happens to row 1. Rows 2 and 3, we're not adjusting at this stage. And row 3, 0, 0, 1, 1, 2. Okay, so now we're still not in reduced row echelon form because we have this leading 1 in column 3, and above it we have 2 entries that are not 0. So we'd like to eliminate them and get zeros where they are. Then we would have a reduced row echelon form as long as we don't do any damage to the left of column 3. But we won't because we'll be adding multiples of row 3 to rows 1 and 2. So okay, so we must look at these 2 entries. We must ask ourselves, what do I have to add to 3 to get 0? Answer is -3, so I should subtract 3 times row 3 from row 1. And at the same step, we should subtract 4 times row 3 from row 2. That will eliminate those 3 and 4 there in column 3. And of course, it will have an effect on the entries in these positions, but we just keep track of that. So we're going to replace row 1 with row 1 minus 3 row 3. And we're going to replace row 2 with row 2 minus 4 row 3. So away we go. Row 1, we're subtracting 3 times row 3. So we're going to get 1 minus 0, 0 minus 0, 3 minus 3, that's the 0 that we want, 5 minus 3 times 1, that's 2, 10 minus 3 times 2, that's 4. In row 2, we're subtracting 4 times row 3, so we get 0 minus 4 times 0, as expected. 1 minus 4 times 0, doesn't disturb that 1. 4 minus 4 times 1, that's the 0 that we expect. 3 minus 4 times 1, and 10 minus 4 times 2, so that's 10 minus 8. And row 3, we're not touching, we're leaving it alone. 0, 0, 1, 1, 2. Okay, so here is our result of those additional operations. So this process, as I mentioned, is called Gauss-Jordan Elimination. It's kind of an extension of the Gaussian elimination process, which gets us to a row echelon form. And this matrix, we can now confirm, is in reduced row echelon form. It has 3 leading ones, and it's apart from those leading ones, within their columns, there's nothing else but 0. So this is in reduced row echelon form. So a remark, the reason for ideas in the course about linear independence and bases and so on, but for now I'll just mention it as a statement. We won't prove it. It's that different sequences of elementary row operations, as we saw, can lead to different row echelon forms. But the reduced row echelon form that one can obtain from any matrix is unique. Okay, so no matter what sequence of operations you choose, and indeed you might choose, there might be different choices. If you started with any matrix which has this as a potential reduced row echelon form, then it's the only reduced row echelon form that it has. So it's not possible to get 2 different reduced row echelon forms, two different sequences of choices about operations from a given matrix. There is a unique reduced row echelon form. Okay, well, what's this good for? I guess it's kind of good for what we were already doing, solving systems of linear equations, because it's kind of even simpler in a way than the row echelon form. So in the row echelon form, the kind of property that we had was that the first variable x1, say, appeared only in the first equation and not in the subsequent ones. The second variable, let's say x2, appeared potentially in the first and second equations, but not in the subsequent ones at the reduced form. But here we have something kind of even better in a sense, in that if you think about the first three columns here in this reduced row echelon form as corresponding to variables x, y, z, for instance, then in the system corresponding to this reduced row echelon form, variable x appears only in equation 1 and not the other equations. Variable y appears only in equation 2 and not the others. And variable z appears only in equation 3 and not the others. So it's kind of simpler than we would have just from a row echelon form. But how that works and what we do with it and why it's actually kind of really a kind of decisive step and not just a kind of incidental additional simplification, we'll see in the next couple of examples. So we're going to go back to systems of equations now. That was a bit of kind of matrix methods and matrix language. We weren't explicitly talking about a system of equations, but let's go back to one. So here is an example. And the problem is to find all solutions of this system, which has 4 variables and 3 equations. And the first step, as usual, is to write down the augmented matrix of the system, and there it is. So in the first row, it has the coefficients 1, -1, -1, 2, 0 of the first equation, and so on. In the first column, it has the coefficients 1, 2, 1 of the variable x1 in all 3 equations. So as usual, the columns here correspond to the variables x1, x2, x3, x4, and to the right-hand side of the system. Okay, the second step, use Gauss-Jordan elimination. So of course, I've skipped a load of detail here. Use Gauss-Jordan elimination to find a reduced row echelon form from this augmented matrix, and there I claim it is. And it is in fact the reduced row echelon form I hope that we had on the last slide. So 2, 4, -1, 2, 1, 2 in the last 3 columns. Okay, so this matrix, of course, corresponds to a new system of equations where the first 4 columns correspond to the first 4 variables, and the last column to the right-hand side of the system. So you can write in this kind of line like that if you want to indicate that there's a sort of column of equal signs there between the left and right-hand sides of the equations. Okay, so this matrix corresponds to a new system of equations, and here it is. So this is just written down by reading it from the reduced row echelon form. The first equation, the first row, has a coefficient of 1 for x1, 2 for x4, 0 for x2 and x3. So it says x1 plus 2x4 equals this 4. Second equation similarly says x2 minus x4 equals 2. And the third equation says x3 plus x4 equals 2. So that's what the 3 equations say, and that's just reading them from the reduced row echelon form, interpreted as an augmented matrix of a system that has the same solution set as the one we started with. Okay, so if we look at these 3 equations, of course we can kind of see, and we already knew, that each of them in turn involves either x1, x2, and x3, and that each of those 3 variables appears in only one of these 3 equations. So we could think, if we wanted to, of the first equation there as describing how x1 depends on x4 in a solution of the system. So I should say how the value of x1 depends on the value of x4 in a solution of the system. This equation says x1 equals 4 minus 2x4. Just rearranging it so the x1 is by itself on the left-hand side. Second equation similarly says x2 equals 2 plus x4. And the third equation says x3 equals 2 minus x4. Okay, so we're saying that this system of equations, which I think we'd all probably agree is a nicer, simpler looking one than the one we started with, it has the same solution set as the one we started with. And what we're saying here is that then, that in a solution, we have one equation each for x1, x2, x3, each telling us how the values of x1, x2, or x3 must depend on the value of x4 in a solution of the system. But we have no equation for x4. We have no equation telling us what the value of x4 should be. So we can say maybe that, well, there's no restriction on the value of x4. It could be anything. But once we've decided what the value of x4 is, then the other 3 are immediately determined by these 3 equations. Okay, so there's a difference kind of in role here between x1, x2, and x3, which have kind of a certain role, and x4, which has a different role. And there's some language that we use to kind of capture that distinction, which is the language of leading and free variables. So the variables whose columns in the reduced row echelon form, so those are x1, x2, and x3, are referred to as leading variables. And the variable x4 in this example, whose column in the reduced row echelon form does not contain the leading one, is referred to as a free variable. Okay, and as I was just saying, the reduced row echelon form tells us how the values of the leading variables in a solution of the system depend on that of the free variable or the free variables if there's more than one of them, which certainly can happen. And the free variable then can assume the value of any real number, and the number of solutions is infinite. So there's one solution to the system for every possible value that you might like to give to the free variable x4. Okay, so this system then has infinitely many solutions because we can choose a value for x4 to be 0 or 1 or 2 or whatever you want. But once you've done that, then the values for the other three are sort of instantly determined. So in this example, we have the concept of sort of describing the general solution, which describes all possible solutions of the system of equations. Oops, sorry, pardon me. I won't do that. Do it where I want it. Okay, so the way that we usually sort of handle the written communication in describing the solution of a system like this is we give the parameter name, and the usual parameter name to choose is t. So we're going to give the parameter name t to the value of x4 in a solution of our system. And we know, for example, that if x4 is t, then x1 must be 4 minus 2t. So x1 is 4 minus 2t. x2 is 2 plus t. x3 is 2 minus t from equation C up here, and x4 is t. So basically for any real number t, assigning x4 the value t, x1, x2, x3, the values 4 minus 2t, 2 plus t, and 2 minus t for that t gives us a particular solution of the system. And the set of all solutions is there's one solution basically for every real number, every choice that you can make for t. So for example, so choosing a value of t, choosing a value for t gives a particular solution of the system. For example, if we put t equal to 1, then we get x1, x2, x3, x4. Equals 4 minus 2 times 1, 2 plus 1, 2 minus 1, 1, which obviously is 2, 3, 1, 1. So putting x1 equals 2, x2 equals 3, x3 equals 1, x4 equals 1 will give us a solution of the system. And you can easily check that that those values do satisfy all three equations from our original system. If we choose t to be something else, we can choose t to be 50, for example. It doesn't matter. We can choose it to be anything we like. If we choose t to be 50, then we get x1 equal to 4 minus 2 times 50. Well, that's minus 96. x2 equal to 2 plus 50. That's 52. x3, 2 minus 50. That's minus 48. And x4 to be 50, of course. And whether you give a solution in this form by like listing the values of x1, x2, x3, and x4, or give it in this form as a sort of vector description of the four values, is absolutely fine. Either way is completely fine, and there's no particular reason to prefer one to the other, I think, apart from just taste. So yeah, so that's how it goes in this particular example. There's a free variable. There are infinitely many solutions, and typically, if you have an example that has a free variable, it will have infinitely many solutions because any real value at all can be assigned to that free variable, and then the others maybe are determined in terms of that. Or if there's more than one free variable, then you have kind of two values to be freely assigned, and the rest might be determined by those. So that's the setup. And I suppose what's going on here geometrically is kind of interesting to think about as well, because we have three equations that we started with in our system. So here's the system as it was originally presented. It has three equations. Each of them has four variables. So the solution set of each of these equations individually is some kind of geometric object in four-dimensional space. Again, it's an example of what's called a hyperplane. So basically, if you want to choose an element, x1, x2, x3, x4, a point of four-dimensional space that satisfies this first equation, basically you can choose x1, x2, and x3 sort of freely, but the value of x4 is determined by those once you've chosen them. So the solution set of any one of these three kind of resembles a copy of three-dimensional real space in the sense that you can choose the first three coordinates freely to pick a point in this solution set, and then the fourth one is determined once you've chosen the first three. What we're saying here is that if we intersect all three of these geometric objects defined by these three equations in R4, then what we're left with is still an infinite set. There are infinitely many points that belong to all three of those geometric regions, and they all have coordinates that satisfy this description for some value of t. And we might recognize that as the sort of parametric description of a line. So in fact, the set of solutions of these three equations simultaneously is essentially a line in four-dimensional space. And a final remark, just in case, I suppose one could be kind of, we might wonder, okay, systems of equations with infinitely many solutions, that's different from the previous example where we had a single unique solution. If we think of something like x plus y equals 1, that's a linear equation in two variables. We can think of it as a system of equations. And actually, let's make it x plus y equals 2, just so that we don't have three ones as coefficients in our equation. We can think of this as a system of equations. It's only got one equation, but it's still a system of equations. Okay, so I mean, obviously you wouldn't really bother writing down the augmented matrix or anything like that because it's only a single equation. But if you did, so its augmented matrix is is 1, 1, 2. And we can put a line between the last column and the rest if we want to. And this is already in reduced row echelon form. It has one leading 1, which is in the first position. And there's nothing else in that column. So according to the designation, x would be a leading variable here and y would be a free variable. The equation says x equals 2 minus y. Okay, so in order to choose a point, the solution of that equation, we can choose y to be whatever we want, but x is then 2 minus y. And of course, we know that the set of solutions of this equation forms a line which passes through, for example, the point 2, 0, the point 1, 1, the point 0, 2. So it's a line that looks like this. And every point on it can be determined by choosing the y value, the y coordinate freely, and then the x coordinate being determined by the equation x plus y equals 2. So this is this is a very simple example. Of course, you wouldn't really even call it a system of equations, or I'm thinking that we have for systems of equations to it. But it's exactly the same sort of situation that occurs in that previous example where one variable is free and the other leading variables are determined in terms of the free one. But the free one can have whatever value you want to give it. And the set of all solutions forms a line in any case where there's a single free variable. Of course, you can have more than one free variable, and then maybe the set of all solutions forms something like a plane. But we'll come back to think about these ideas in due course in any case. Okay, so that's a system with a free variable. And one of the things that kind of comes out of this is that if you have a system of equations in which every variable is a leading variable, then basically the columns corresponding to the variable names in the reduced row echelon form will just have 1, 1 and otherwise be full of zeros. And the value of each variable would be completely determined in the solution. So there'll be a unique solution. Okay. If you have a free variable, then already you have infinitely many solutions. So you can't have, for example, a system of equations which has exactly 2 solutions or exactly 4 solutions or exactly 20 solutions. If it has more than one, it has infinitely many. And that's already, I think, something that isn't obvious, but kind of comes out of this geometry. Okay, one more thing to mention in this lecture, and then we will leave it for today, which is about so-called consistent and inconsistent systems. So here's another example. A system of equations. Here it is. 3 equations x, y, z. Three variables. And of course, suppose we want to solve this system. So we would do the obvious thing. We'd apply elementary row operations to the augmented matrix to get a row echelon form, or preferably a reduced row echelon form if we want to. But let's see what happens when we do that. So our augmented matrix has 3, 2, minus 5, 4 in its first row, 1, 1, minus 2, 1 in its second, 5, 3, minus 8, 6 in its third. And we want to get it into row echelon form initially, and then into reduced row echelon form possibly. So I guess our first strategy, let's just go through this since we won't be doing too many more of them. Our first strategy is to get a 1 up there in the top left. What's there at the moment is a 3. And we could divide row 1 by 3, but that would introduce denominators. So let's make our lives easy for ourselves by not doing that, by instead swapping row 1 with row 2. So if we swap row 1 with row 2, then we have 1, 1, minus 2, 1 in the first row. After that, we have 3, 2, minus 5, 4 in the second row. And we have 5, 3, minus 8, 6 in the third row. Okay, fine, that's good. That's what we wanted. We have our 1 here now on the top left where we wanted it. We can now use that to clear out the rest of column 1. And when we do, so we'll subtract 3 times row 1 from row 2. One, 1, minus 2, 1, still in row 1. In row 2, now we have 3 minus 3 times 1, that's 0. 2 minus 3 times 1, that's minus 1. Minus 5 minus 3 times minus 2, that's minus 5 plus 6, so it's 1. And 4 minus 3 times 1, that's 1. Okay, and we also want to clear out the 5 there in the lower left corner. So we should replace row 3 with row 3 minus 5 row 1 to clear out that 5. And when we do, we get 5 minus 5 times 1, 3 minus 5 times 1, minus 8 minus 5 times minus 2, that's minus 8 plus 10, and 6 minus 5 times 1, which is 1. Okay, fine. We're in good shape now. We have a column 1 cleared out. We should now look in row 2 and see where and look in column 2 below the first entry. And indeed, there are non-zero entries there. So we should try to get a 1 in that position that I've circled. And we can do that easily, for example, by multiplying row 2 by minus 1. We get 1, 1, minus 2, 1. If you want, you can skip this step. You know, do a couple of steps together. That's absolutely fine. 0, minus 2, 2, 1. Okay, and having done that, that's going to be our second leading 1, and we should clear out column 2 below that second leading 1. And when we do that, we get 1, 1, minus 2, 1. What are we doing? We're adding 2 times row 2 to row 3. So row 2 is not going to change, 0, 1, minus 1, minus 1. But in row 3, we're adding 2 times the entry above it in row 1 to each entry of row 3. So we get minus 2 plus 2, that is 0. 2 plus 2 times minus 1, that's 0 as well. And 1 plus 2 times minus 1, that is minus 1. And this is something that hasn't really happened before. So remember that all the time we have this kind of line separating the right-hand column from the rest of the matrix. So what we're finding here is that we're actually getting the leading 1 in the position, in the column corresponding to the right-hand side of our system of equations originally. Okay, so what happens when you look, if the usual step at this stage would be to go to row 3, look for the leading 1 there, and there is no leading 1 in row 3 in column 3. It's actually in column 4. So this matrix, the last version of it here, the last step here would be to multiply row 3 by minus 1, I guess, if you wanted to. Let's write it in. Just to be clear. This is a reduced row echelon. It's a row echelon form. It's not reduced. And there's nothing wrong with it as a row echelon form. But if we think of it in terms of how it relates to our system of equations, the fact that we have a leading 1 there in the right hand, the column corresponding to the right hand side, kind of tells us that the equation corresponding to that row is an equation that can't really have a solution. Well, it can't have a solution at all because it says 0x plus 0y plus 0z is equal to 1. So if we have this position where we see a 1 turning up, a leading 1 turning up in the right-hand column corresponding to the right-hand side of our equations, it tells us that that any solution to our original system would also have to be a solution to this equation, which has 0 on the left-hand side and a non-zero quantity on the right-hand side, and that certainly cannot be satisfied. So here's our row echelon form. The system of equations corresponding to this row echelon form has as its third equation 0x plus 0y plus 0z equals 1. And that equation certainly does not have solutions. There's no assignment of numerical values to x, y, and z that can make 0x plus 0y plus 0z equal to anything but 0. So our conclusion is the system has no solution, because any simultaneous solution of the equations in the original system would have to be a solution of this thing as well. And so a system of linear equations is called inconsistent if it has no solution. Okay, if there's no assignment of real values to the variables that would satisfy all the equations, and a system which has a solution is called consistent. So just on the topic of inconsistent systems, I guess this business about the leading one in the right-hand column, that's kind of how it would manifest, how you would learn in a process of Gaussian elimination that your system is inconsistent. What it means in geometric terms, if we just look at a quick example, and if you want to give yourself kind of a straightforward example, you know, the kind of expected situation, if you take a system of equations, is that you, well, particularly if there are at least as many variables as equations, you expect it to have a solution generally. And the sort of exceptional situation then is where it doesn't have a solution. So if you take an example like this in R2, like if you take the lines x plus 2y equals 4 and x plus 2y equals 6, for instance. That's a pair of lines in R2. And of course, we can recognize from the way their equations are written that they are parallel to each other. So for example, the point 4, 0 is on the line x plus 2y equals 4. The point 6, 0 is on the line x plus 2y equals 6. The point 0, 2 is on x plus 2y equals 4. The point 0, 3 is on x plus 2y equals 6. So the two equations look somehow like this. The two lines look like that, they're parallel, they don't intersect, so there's no choice of coordinates x and y that simultaneously satisfy both equations, because x plus 2y cannot simultaneously be equal to 4 and to 6. So in that example, the previous slide, so there it was, it wasn't obvious by looking at this one that these three equations somehow represent geometric structures that have no common point of intersection. We have to do a little bit of reduction, we have to do a little bit of manipulation, a little bit of adjustment of the coefficients to be able to see that. But essentially that's what we're doing when we realize that we have this leading one in the fourth column in our row echelon form. So each of those equations actually represents a plane in R3. Okay, so basically it's sort of a copy of R2 living inside R3. So the kind of expected situation, if you have three planes in R3, is that the intersection of the first two of them would be a line, and the third one basically would intersect that line in one point, and there'd be a single point of intersection of all three. But that doesn't have to happen. So for example, I'll try to draw a picture which hopefully might not look too bad, but it probably would look great. So there's a single plane in R3. It's a sheet, it's like a copy of R2 inside R3. If we have a second plane, the usual sort of setup is that it would intersect that one somehow along a line. So there'd be a sort of line of intersection between the first two, which would look like this. And if the third plane was in some different direction that that line sort of cut through it at one point, that point would be the unique simultaneous solution of all three equations. But the other thing that can happen is that that line could actually be parallel to the third plane. So the third plane could somehow be like this. Okay, this is not a good picture, but hopefully maybe you can sort of see what I mean. So that basically they sort of each pair of the planes intersects each other in a line, but those three lines don't have a common point of intersection. So this is a kind of geometric setup with three planes that sort of intersect each other, creating kind of a triangular tunnel or something. And so they don't have a common point of intersection, although each pair of them intersects in a line. That's the sort of thing that can happen geometrically when you are dealing with a system of three equations in three variables that don't have a common solution. Of course, another thing that could happen is that all three equations could intersect each other in all three equations could share a single point of intersection, or they could share a whole line of an intersection, and that would be the case where you'd have a free variable. So certainly you can have a system of equations that doesn't have any solutions, and that happens basically because the objects, the equations define geometric objects that just sort of miss each other and don't have a common point of intersection. But in terms of elementary row operations and our methods for attacking systems of linear equations, the way that an inconsistency would emerge would be as it did in this example, that you'd see at some point you'd get a row which has all zeros in the positions corresponding to the variable names, but has a non-zero entry in the right-hand side. And such a row tells us that there's an inconsistency in the system. There's that the system can't have a simultaneous solution. So basically, as soon as you see a row like that turning up in your process of elimination, you can stop. At that point, you can announce that the answer is there's no simultaneous solution of all the equations in the system, and there's no point in doing any further reduction. It doesn't really give you any valuable information. You already know there's no solution. So in this example, you'd report the system is inconsistent. It doesn't have a solution. So those are basically kind of the three things that can happen with the system of linear equations. You can have a unique solution if every variable is a leading variable and the system is consistent. You can have infinitely many solutions if there's at least one free variable, but the system is consistent, or you can have no solution if the system is inconsistent. So next time we'll come back and kind of revisit these concepts one last time and see what else Gaussian elimination is good for. But that's it for today. So thank you very much and see you next time.